I am Professor Jade Mitchell, and in this module, I am going to discuss cost-benefit analysis and the use of decision trees for such analysis in QMRA. By the end of this module, you will understand how a cost-benefit analysis can be used to evaluate risk management decisions. You will also understand and be able to graphically structure a cost-benefit analysis problem using a decision tree. You will learn to solve a decision tree based on expected value and also use decision trees to calculate threshold risk or probabilities that can be used as the basis for a risk management decision in the absence of other criteria. A few key terms for this module are cost-benefit analysis, cost-effectiveness, and marginal cost-effectiveness. Cost-benefit analysis is a process used to measure the benefits of a decision or taking action minus the cost associated with taking that action. Often it results in a cost or benefit ratio when you divide the cost by the benefits. Cost effectiveness analysis is the way that we do economic evaluations related to health. And though I'll use these terms interchangeably in this presentation, they are a bit different when it's difficult to quantify the benefits. I will refer you to Dr. Gurian's presentation and module on monetizing benefits and valuing risk. Third, marginal cost effectiveness. This is the additional cost of a strategy divided by the additional health outcome it achieves, and thus pertains to situations where there is a choice between two or more effective risk management strategies. So why is this important? Risk reduction strategies cost different amounts of money, and because they have different costs associated with them, we need a means to evaluate them in terms of their benefit so that we can select an appropriate risk reduction or risk management strategy. Second, methods that consider decision making under uncertainty are required since risk is a probability. So I will demonstrate how using a simple cost-benefit analysis may not be as effective as using one of the techniques that we'll go through in this module. The benefit to you is that you will be able to evaluate strategies and make recommendations to mitigate risk based on cost effectiveness or cost benefit. This module explains how to select an appropriate risk management strategy. Therefore, it fits into the green bubble under risk management and quantitative evaluation of risk management strategies. So let's begin. Cost benefit or cost effectiveness is usually established for a risk management strategy by dividing the cost of the strategy by the amount of risk reduction. Risk reduction may be quantified using several different metrics, which were discussed in Dr. Gurian's module. For our example, we'll use lives saved as a risk reduction measurement. So the number of lives we can save is a way that we can benefit, or the way that we can describe the benefit of a particular risk management strategy. Usually, we want to pick the most cost-effective solution, and that's the one that's going to cost the least per measure of risk reduction, purely based on an economic evaluation. We generally all want the more cost-effective solution. And it is customary for risk assessors or engineers to calculate the cost effectiveness and then stop there. But I'll show you in an example why we may want to do more. So, in our example, if we're looking at arsenic in drinking water, we have two different risk management strategies. The first is to set a standard for arsenic at 20 micrograms per liter. And we know that this will save 47 lives per year for a cost of $120 million per year. So to calculate the cost effectiveness for this strategy, we would simply divide $120 million per year by 47 lives, and we come up with a cost effectiveness ratio of $2.6 million per life saved. The second strategy is to set a standard at 10 micrograms per liter, where we can save 55 lives per year. The cost of this strategy is $300 million per year. So to calculate the cost effectiveness of this strategy, again, we would divide the cost by our benefits in lives saved, and we would get $5.5 million per life. What we have to consider is that most of those 55 lives would have been saved at the 20 microgram per liter standard. We know specifically that 47 of those lives would be saved. So we couldn't just evaluate the 47 lives and the 57 lives for the 20 micrograms per liter versus the 10 micrograms per liter purely on a basis of cost effectiveness. In this example, we would want to look at the marginal cost effectiveness. So again, the marginal cost effectiveness is the difference in the cost divided by the difference in the benefits, so that we know for the additional lives we're saving, how much those lives are valued at. And for this example, we would have 300 million minus 120 million divided by 55 lives minus 47 lives, which would end up giving us 180 million divided by 8 lives. And that is equivalent to $22.5 million per life. Typically, we have a certain value that we assign, the value of a statistical life, from your risk valuation modules. And if we assigned a value of $6.3 million per life as our basis for the VSL, then we see that it would not be justified to go to 10 micrograms per liter, because the marginal cost effectiveness of going from 20 to 10 greatly exceeds $6.3 million per life. When we just look at those cost effectiveness ratios for both 10 micrograms and 20 micrograms per liter, either of those options would be justified because they're both under $6.3 million per life. So hopefully you can see from this example that simply looking at marginal cost effectiveness, especially for multiple risk management strategies that maybe we'll call nested, it's important to look at how many additional lives will be saved and what the cost of those additional lives will be before making a decision. Next, I'll show you how to structure your cost-benefit analysis using a decision tree. The reason that we want to structure it with a decision tree is because the decisions that you're making about risk have some uncertainty associated with them. Risk itself is a probability. So, in developing a decision tree, we would outline our choices being our risk management strategies, and put those in rectangles. Then we would look at the possible states or chances that could occur, and we would put those in ovals. So if we have a strategy to reduce risk, our chance is that a person may die or not die. And those would be what we would put in the states, for example. Finally, at the end of our tree, we would enumerate the outcomes based on the risk management strategy defined in the boxes and the chance of an adverse outcome occurring. Next, we would assign probabilities associated with those states or chances. We can call our probabilities P for short. And then for each chance, there is a probability of the outcome occurring, and then the complement, which would be the probability of the outcome not occurring. So we would assign a probability P for the outcome occurring and a probability of 1 minus P when the outcome does not occur. And then as an example, we can put in the cost and the benefits for our outcomes and use expected value for each choice in order to make the decisions, where the expected value is going to be P times the outcome associated with the adverse outcome occurring, and then you're going to add 1 minus P times the cost or the expected value of the outcome not occurring. And you will continue to do this for each option and use that as the basis for selecting an option. When we're making a decision based on expected value, we want to choose the outcome with the greatest expected value. This means that we're going to want to put our benefits in positive terms and our cost in negative terms. There are ways to use decision trees on an all-cost basis. And if we were doing such, we would want to choose the least costly option. But if we're truly doing a cost-benefit analysis, our benefits would be positive, our costs would be negative, and then we can use expected value to choose the option with the greatest expected value. So in order to solve our trees, first we accept that we're going to make our decision based on expected value. Second, we are going to calculate the expected values for each node, and at each decision node or square, we're going to select the maximum expected value. At each probability node, we are going to evaluate the expected value and then use that expected value to keep moving backwards until we get to a decision node where we're calculating the expected value for the decision itself. In order to do this, we're going to work from right to left and fold the trees backwards. The equations to calculate expected value are basically this. The expected value for the option is always going to be the sum of the probabilities times the outcome, as I showed in our graphical sketch previously. Next, I will walk through an example. In this example, we are deciding where to hold a party. This is the party problem. And we want to decide whether we should hold the party inside or outside. The expected value from holding it inside is going to be $50. If we hold it outside, there is a chance that it will rain. And we can assign that chance of being 0.3, where it not raining is going to result in a probability of 0.7. If it does rain, we can make another decision. Should we cancel the party? If we do cancel the party, yes, the value of that outcome is 0. If we don't cancel the party, there's another chance that we should consider, and that is, will people come? Here we assign the probability that people will come at 0.8 with an expected value for the outcome of being $25, or the value for the outcome of being $25, and then no, if no one comes, the probability again is going to be the complement, 1 minus 0.8, so 0.2. And here we're going to lose some money because, say, we purchase things in order to have refreshments at the party. So we're going to assign that outcome -$10 if people do not come. So now that we've set up the problem, we can start to calculate expected values moving from left to right and folding backwards. The first chance node that we're going to evaluate is, will people come for the outside party, given that it might rain. So we have 0.8 times 25 plus 0.2 times -10, and we get an expected value at the chance node, will people come, of $18. Based on this expected value, we would compare that $18 to $0 for canceling. And that allows us at this decision node to make a decision not to cancel the party. So we can cross out the yes, cancel, because that is less, that will result in less than $18, which is the maximum expected value here. Next, we're going to continue to fold back from right to left. And now we have a chance node for, will it rain? If it does not rain, our probability is 0.7. So if we multiply 0.7 times 100, we will then add the yes, it does rain expected value, which will be $18 from our previous expected value calculation, times 0.3, which is the complement of 0.7. And when we do that math, we get an expected value for the rain chance node at $75.4. So now we can make a decision at our next decision node where to hold the party. If we hold the party outside, our expected value for that outcome is $75.4. If we hold the party inside, our outcome is simply $50. So we're going to choose to hold our party outside and cancel out the option to hold it inside. This is one simple example of how we can use decision trees to do a cost-benefit analysis. I will continue in the next video with the second use of decision trees in QMRA.